do some nuclear physics, huh? Let's do some nuclear physics. Yes. So, nuclear energy generation. You keep sighing.
I just realized that that notebook is full.
Well, okay then.
Shower time. Door. Understandable.
That's not good.
All right, well, while he's gone, I can be slowly and carefully drawing this diagram. Sketch of distance in Fermi, 10 to the minus 15 meters, which is about the size of a proton or the size of an atomic nucleus, between a pair of protons. So, and it is just a rough sketch, but 10, 20, 30 Fermi. Distance along the r-axis, radius, and so I will first kind of draw in the curve, and then we'll decorate more. And this is a rough sketch here. Yeah, something like totes. So what this is supposed to be a plot of is the potential energy of interaction as a function of r, distance between two protons. And that horizontal line is zero potential energy. And the units here are millions of electron volts. And I may not get exactly the labeling right here, but 30, 40, 50, this is about right. 60 MeV. And see how this goes. Yeah, it's not quite working out there, so I'm going to have to redraw this part. So maybe you should wait until I'm a little further along before you draw yours. I'm going to go through that one right there. That's at about 10 Fermi and about 25 MeV. Actually, I wouldn't have had to do that come to think of it, but whatever, let's just stick with that. So what that part represents is the Coulomb repulsion. In other words, the closer they are together, the higher their interaction energy is because they're pushing off on one another. And so this is the Coulomb repulsion energy. Which goes like 1 over r, right? Because the Coulomb force is 1 over r squared, which means its potential energy goes like 1 over r. So that's a 1 over r dependence there. If all you had was the Coulomb repulsion, the potential energy would just keep getting bigger and bigger as the two particles got closer to one another. But the protons are close enough to one another, they can start feeling the short-range strong nuclear force, which is attractive rather than repulsive. And so if they're close enough to one another, then the potential energy goes negative because there is a strong force attraction between the protons. And 25 MeV here is supposed to just be the energy of incoming proton proton. Should have said this to begin with. R is the separation between them. So as they get closer and closer to one another, they have a higher and higher potential energy of interaction. If they got close enough, then the strong nuclear force takes over, which is attractive, and makes the interaction energy go negative. So if only they could get close enough to one another, they could attract one another instead of repelling one another. That's the key to nuclear fusion, is that if you can get the nucleons close enough to one another, the strong force attraction, which is a very short-range force, can overcome the long-range Coulomb repulsion and allow them to bind together, to fuse if the conditions are right. Yeah?
Is there any reason why the strong nuclear force is constant rather than
We're just making a simple model here. Yeah, it's much more complicated than this. This is, we're just saying, yeah, you know, we're just modeling it as an attractive well, essentially. It's you know, think of back to like the infinite square well kind of stuff, except it's not infinite. It goes up, but then it does this. So this is, we can think of it as like what you did when we did like infinite square well, and then there's finite square wells, all that kind of good stuff in physics 280. Better yet, physics 380, but you guys haven't had 380 yet, is that right? You guys?
Yeah.
Yeah, you too. Okay, but that too, you know, basically quantum well here is what we're talking about. So more to come, but what we know from 280 is enough here to think about what's happening. So if this was a classical problem, then what we would find is our incoming proton would get to this point and turn around, because to go any further than that, you would have negative kinetic energy, right? In other words, the total energy stays constant, and since E is K plus U, then that says K is E minus U. So K is equal to 0 when the energy is equal to the potential energy of interaction at that point right there. So this is where, classically, the incoming proton would stop and then turn around. That's what we call the classical turning point. So that value of R. So in other words, in this case, they get about 10 Fermi from one another and then reverse directions and start flying apart from one another. So actually, I was start decorating from here and then writing all the words I'm going to write. So any questions at this point? So let's add words, shall we? Yes. So consider a nucleus of charge Z1e. So Z1 is the atomic number of that nucleus, the number of protons in the nucleus. E is the magnitude of the charge on an electron. So E is a positive number. The charge on an electron is minus E, not the base of the natural logarithms. So the nucleus with Z protons, Z1 protons in it has charge Z1e. It collides with a nucleus of charge Z2e. Such that a nuclear reaction takes place. E.g., for example, they might fuse to form a larger nucleus. To happen, they need to get close enough to feel the strong force attraction strong nuclear force attraction. Strong nuclear force is one of the four forces of nature. What are the others? The strong force, the weak force, the electromagnetic force, and gravity. Yeah, so to feel the strong nuclear force attraction.
There's only 3 electroweak.
What's that?
So there's only 3 electroweak forces.
Well, yeah, if we are at high enough energies. To do so, they need to overcome the so-called Coulomb barrier, i.e., overcome their mutual electrical repulsion. It's a good thing that they do have to do that, because otherwise nuclei in this room would fuse with one another and we wouldn't be having this conversation. The room wouldn't be here either, for that matter. So classically, notice, for that to happen, the energy would have to be up here. They'd have to have enough energy that it exceeded the maximum potential energy of the Coulomb interaction. They'd have to get all the way touching one another. What we will see, though, is that quantum mechanics helps out here. In other words, they tunnel through the barrier and fuse with each other. As an example, tunneling. Yay, quantum mechanics and tunneling. What's that?
It's a joke from a cartoon called Avatar. There's a song that they have called Secret Tunnel.
Secret tunnel? Ah, okay. All right, I like it. It's not that secret we know about.
It's not secret. That's a very big Zach Claytor joke.
Is
So
it?
if you ever was talking about tunneling,
Yeah.
you should be like, secret tunnel. And then he'll be like, holy shit, Dr. Harmon. I'm not even joking. Do it the next time you see him. I swear.
I'm just going to post on his Facebook page. I'm just going to say
Secret tunnel?
secret. I'm going to say in astrophysics today. ... Secret tunnel. I was told you would react to this. Let's see what happens.
Do it. Actually, no, like actually do it. Nicole has you as a friend. I'll know.
Okay. Yeah. So, what we'll do is two-body problem, let's replace it with an equivalent one-body problem, because that's generally helpful. As usual, we can replace our two-body problem with an equivalent one-body problem in which a particle having reduced mass mu approaches a fixed potential at the origin. So we imagine that we've got just a nailed potential at the origin, space-time nails are holding it in place, and then a reduced mass comes in under its influence. As usual, we can replace our two-body problem with an equivalent one-body problem. In which I lost it. In which a particle having reduced mass mu m approaches a fixed potential at the origin. So fixes in. Classically, the distance of closest approach is where your kinetic energy K equals 0. i.e., since E equals, as we said before, E equals K plus U, it's where K, I'm sorry, it's where, what do I want to say? It's where K equals E minus U equals 0, or in other words, it's where what do I want to say? It's where, yeah, E equals U, essentially, right? E equals U. When the particles are far apart, U is equal to 0, so E is equal to K far away. The incoming kinetic energy, in other words. The kinetic energy that's flying in with far away is its total energy. Which will be 1/2 uv squared for our reduced mass. So 1/2 uv squared is the incoming kinetic energy. We set that equal to the potential energy at a given r that will be the r for which it stops and turns around. which we'll call R subclassical, is R equals R classical such that 1/2 mu v squared, 1/2 mu sub mv squared is equal to their potential energy of interaction, which will be the product of their charges divided by 4 pi epsilon naught R classical. In other words, the Coulomb potential energy is Q1, Q2 over 4 pi epsilon naught R, and Q1 is Z1e and Q2 is Z2e, so Z1, Z2 e squared over 4 pi epsilon naught R classical, equaling the incoming kinetic energy, 1/2 mu mv squared, will allow us to solve for R classical, the classical turning point, the closest we get to one another before they stop and turn around. Or in the one-body problem, the closest that the reduced mass gets to the fixed potential at the origin before it stops and turns around. In other words, we're solving for that point right there, the value of R equals R classical. Okay, any questions about that?
But again, where does Z1 look like? I know
So we've got, I know before I was talking about it, because this is drawn for 2 protons basically, but in general, we would have, there's nucleus 1, it's got Z1 protons in it. There's nucleus 2, it has Z2 protons in it, and if they're a distance r apart, right, so Q1, the charge on the first nucleus, is number of protons times the charge on one proton. Q2, number of protons times the charge on one proton. So Q1, Q2 is Z1e times Z2, or Z1, Z2, Z2 squared. Okay? So, classically, we would think for them to fuse, they have to have enough energy that it's over the top of the barrier. The minimum energy they could have would be such that they reached all the way to here so that now they started feeling the strong force. So we could estimate what temperature that would take by saying, okay, well, let's set that incoming kinetic energy equal to what we would expect from the thermal energy. Just set that equal to 3/2 kT. So we can estimate the temperature. Required for fusion to occur classically by setting 1/2 mu mv squared equals 3/2 kT. The thermal kinetic energy. Part of it. Of course, it wouldn't have to be quite that hot because at any given temperature, some of the particles are moving faster, some are slower. So you could be lower than that and still have some particles moving fast enough to fuse. But we're just trying to get an estimate. So let's just assume that we want the average kinetic energy to be high enough to overcome the barrier. And that would mean, yeah, we'll have good healthy fusion going on here. A lot of particles will be fusing. We're going to find this gives a value that's way hotter than the center of any star. So that can't be what's going on. Using R equals 1 Fermi equals 10 to the minus 15 meter for the psi size of a typical nucleus, and the approximate range of the strong nuclear force, not a coincidence. Nuclei are that size because that's about the range over which the strong nuclear force acts. We find R classical is 2z1 z2 e squared over 12 pi epsilon naught k, we'll call it T classical. We're setting that equal to 1 Faraday. So in other words, what we've done is we've put 3 halves kt equals z1 z2 e squared over 4 pi epsilon naught R classical, and then solve for R classical. So then T classical is z1 z2 e squared over 6 pi epsilon naught times the Boltzmann constant k times R being 1 Faraday. So let's suppose it's two protons we want to fuse. What's Z1 for a nucleus consisting of a proton? 1. And what's Z2?
Also 1.
Also 1. So for 2 protons, Z1 and Z2 are 1. With 2 protons, Z1 equals Z2 equals 1. This yields, when you run the numbers, the temperature required for fusion would be around 10 billion Kelvin. Woo! Woo! Hot!
Not even bad. It's like Luke one.
Taint nerd. Why, that rock come from? They call that autumn.
The 5th season.
However, in the middle of the sun, temperature's around 16 million Kelvin, not 10 billion Kelvin. So what gives? It occurs to me, that's from German actually, because in German they have this, this idiom where when they say there is or it is, they say es gibt, which literally means it gives. And it's just an idiom. So I think what gives probably come from was gibt, is what you would say in German. So I think that's actually, that just dawned on me, that's where they come from a German idiom. So what gives? You know, English is a Germanic language, so what gives is quantum tunneling. Quantum tunneling is what gives here.
How hot do the cores of like red giants get? Like blue giants?
They will switch to helium fusion when they reach 100 million Kelvin. So even then we're talking like a maximum of 10 to the 8 Kelvin before helium fusion kicks in. Carbon fusion kicks in at about 600 million Kelvin. You do get temperatures in the billions of Kelvin, and the very last stage is when a star is about to, a high mass star explodes as a supernova. Then you get temperatures that high, where you're fusing heavy elements. But nowhere near that when you're fusing light elements broadly in sequence. So, yep. So the idea is that, remember that in quantum mechanics, when you have, for example, so if you have the infinite square well, then psi is 0 outside the well, because you've got an infinite barrier there. Whereas if you have a finite square well, then what happens is that psi does not go to 0 outside the well. There's a region where the wave function is not 0, even in the classically forbidden region. Classically, a particle with this energy would not be able to leave the well because its kinetic energy would be negative, but in quantum mechanics, solve the Schrödinger equation, it actually extends to infinity, but in practice, not, where there's significant probability to find the particle outside the well. And if you had, say, a pair of finite square wells, then you could have a situation where, I better get closer than that. There's a pair of finite square wells. So I might have a situation where I'll draw it the other way around. You could have a situation where you'd like start that. I don't want to try to draw the whole wave function. You could, if you put in the time, well, basically you can get a solution for the time independent problem. Those would be symmetric, but if you have a particle that starts in one well, you find that its wave function leaks over into the other well, and in fact, what you would find is over time, it'll exchange back and forth, where even though you started in one well, there are times when the wave function's amplitude is higher in the other well, then it switches back and forth. Classically, if you start the particle in one well and it doesn't have enough energy to cross the barrier, it always just stays in that well. But quantum mechanically, the particle will tunnel back and forth between the two wells, even though classically that would be impossible. Because you can think of it as the wave function doesn't go to 0 by the time you get through the barrier, so there's a finite probability of finding it on the other side of the well. And the idea with fusion here is that the incoming particle, you have to describe it as a wave, and the wave's amplitude diminishes in the region where classically the kinetic energy would be negative. But if you get close enough, there can still be a reasonably large amplitude of the wave function inside the well, and so the particle can tunnel in. It can find itself inside the well, and then fusion can happen. So qualitatively, that's what we're looking for here, is if the particle's energy is enough so that it gets reasonably close to the barrier classically, then the wave function can have a significant amplitude inside the well, and it can tunnel in, and they can say, oh, hey, we found each other and fuse, even though classically they would never be able to do that. So the wave nature allows them to fuse in situations where classically they would never be able to do it. Any questions? So I'm going to wave some chicken feet here. I'm going to not derive everything we're talking about because, it's just the way it is. We can't spend all our time on this. So I'm going to make a sketch here where on the top I reproduce what we had over there. So in other words, this is R again, this is U again. Excuse me. Thank you, appreciate that. So there's the potential energy. And on the bottom here, I'll sketch the wave function. There's E incoming. Excuse me. So, imagine this were an infinite square well. In that case, we would just have a simple sinusoid that went to 0 on both edges of the well. In this, so it's really a three-dimensional problem, right? Because the particles are moving in 3 dimensions. But we're just looking at the radial part. And effectively then, it's as though it's kind of like a semi-infinite square well. In other words, effectively, you can think of, because the particle can't go to r less than 0, effectively it's like there is an infinite barrier at r equals 0. So the wave function goes to 0 at the origin. If it were an infinite square well, this might be, say, an energy corresponding to one wavelength fitting inside the well. But if it's a finite square well, then that's not what happens. So you can have, okay, well, it doesn't quite go to 0 at the edge of the well there. It goes to 0 a little bit before that, and so it's not 0 at the edge of the well. This is from solving the Schrodinger equation in detail, which you come up with all of this. And meanwhile, outside, if you're very far away, the particle has a certain kinetic energy. What does the wave function look like very far away? So this is, you don't remember, okay? So,
Shouldn't be always 0, because it's not,
it's going to look like what?
It's always 0 because there's no.
No, it won't be 0. It won't be 0. If it's got some energy, right? The energy is p squared over 2m, right? Or 2 mu here. Let's be consistent with this being a one-body problem. The energy is p squared over 2 mu, where p is the momentum, right? So psi far away should be of the form, it's going to look like a wave function that represents a particle having a given momentum. Do you remember, what do those look like? They look like e to the plus or minus ipx over h bar. E to the ikx. Remember that complex exponential sinusoids are eigenfunctions of the momentum operator, so that they have well-defined momentum. Remember that the p operator is minus I h bar ddx, right? That's the momentum operator, is minus I h bar ddx in quantum mechanics. So if I apply, I'll put a hat on it to say it's an operator. So if I apply it to a wave function of the form e to the I times p times x over h bar, well, that's minus I h bar ddx of e to the I p x over h bar. What's the derivative of e to the ipx over h bar? this is minus IH bar times IP over H bar, e to the IPX over H bar. H bars cancel, minus I squared is 1. So this is P e to the IPX over H bar. In other words, it's an eigenfunction of the momentum operator with eigenvalue P, right? We have a condition where the operator applied to psi is the eigenvalue P times psi. So e to the IPX over H bar is a wave that has momentum P, particle has momentum P. I said e to the plus minus IPX because, it could go left or right, is what it comes down to. So you could have it P or minus P if you like. Or I could just say e to the IPX over H bar and P could be positive or negative. Take your pick. So far away, psi should be of the form e to the IPX over H bar, which you can have some amplitude attached to it. It's not normalizable. I don't want to worry about all that. So it's a sinusoidal function. I say sinusoidal, it's really complex exponential, but complex exponentials are sines plus cosines. So they're, it's cosine plus I sine. So it's sinusoidal. So the real or the imaginary part is a sine wave or a cosine. It's a sinusoidal wave. So, the wavelength, how's that related to the momentum? Remember the de Broglie relation, de Broglie, or whatever, however you say it. Lambda is what? As you well recall, lambda is h over p.
That's right.
Planck's constant divided by the momentum. So as the momentum increases, what happens to the wavelength? It decreases. As the kinetic energy increases, therefore, since it's p squared over 2m, the wavelength decreases. So far away, the wave function ought to be a sinusoid. As you get closer in, the momentum is diminishing because it's slowing down, so the wavelength's increasing. So in other words, qualitatively speaking, if we just drew, say, the real part of the wave function, I'm gonna cheat. So I'm gonna go through here, and then what we'll see is the wave function ought to do something like this. In other words, the wavelength should get longer as you approach the barrier. Short lambda far from the well. Longer lambda closer to the well. Since KE and P are smaller there. And the wave function psi is sinusoidal outside the well. Where the classical KE is greater than 0. So what happens when the classical kinetic energy is negative? Instead of a complex exponential, you get what? I'll be lying a little bit, but what's that? So outside the well, where the classical kinetic energy is positive, you expect to see a complex exponential wave function. Now, strictly speaking, the potential has to be constant for it to be a complex exponential. We are, without saying it, what we're alluding to is what's called the WKB approximation, where you say, okay, I'm going to assume that the wave function is, instead of just e to the I px over h bar, is e to the I, a variable function, p is a function of x, if you will, x over h bar. And you can use that to get an approximate solution to the Schrodinger equation. And we're not going to go through all that, but that's essentially what we're doing. We're saying that the wave function is a sinusoid with varying wavelength as you approach the well here. So in the finite square well, it's sinusoidal inside the well. Outside the well, it's sinusoidal. It's like an e to the I kx kind of thing. Outside the well, you get rid of the I in the exponential. It's an exponential decay outside the well. So we get exponential-ish decay where the classical kinetic energy would be less than 0. I say exponential-ish because, strictly speaking, it's only a complex exponential with a constant coefficient if the potential is constant over that region. Since it's not, it looks like a variable function here in the argument, but you don't have the I there anymore. So, in other words, it wiggles outside and it decays in regions where the energy is less than the potential energy. When you're in the well again, you're back to where the energy is greater than the potential energy, so it switches back to a wiggle. So in other words, ultimately what we've done is we've stitched together two wiggle wave functions where the classical kinetic energy is positive, where the energy is bigger than the potential energy, and you have to stitch them together with an exponential decay, and the stitching together means I have to match the two boundary conditions. Psi has to be continuous across the boundary. So, you know, my sketch is not a rigorous solution, but it looks something like this. So the point is, then, that in quantum mechanics, you get some wave function inside the well, even though classically, you could not get through that barrier. Classically, the particle would stop and turn around here. Quantum mechanically, when you solve it and put in the boundary conditions, there's a non-zero amplitude for the particle to appear inside the well, even though classically you could never get there. That's the key to nuclear fusion in stars happening at much lower temperatures than would be required classically. You don't have to be hot enough to overcome the barrier classically. You just have to be hot enough to have a significant amplitude for the particle to tunnel in, to find itself inside the well. Okay? Any questions?
So the whole exponential decay is the one that's happening?
Yeah, the tunneling is this exponential decay, but it hasn't gone to 0 because to go to 0 you have to take an infinite distance. So if you are only, if the classical turning point were way out here, if your energy is lower, right, then it would exponentially decay over a much longer distance, and the probability of finding it inside the well becomes so small that you'd have to wait a long time for it to accidentally really be there, so to speak, in the quantum mechanical sense. Of course, it's always probabilities, but in other words, if the probability of finding it inside the well is too low, then the nuclear reaction rate would be vanishingly small. Hardly ever does it actually tunnel in, so to speak. the higher the energy, the shorter the distance over which the exponential decay occurs, the larger the amplitude inside, the higher the chance that the fusion will actually take place. And so after the break, we'll hand wave a bit about the condition of what it is for, what is the condition where this amplitude is big enough to have a reasonable probability that the tunneling actually leads to fusion, is what it comes down to. It always could in principle, but at room temperature, sure, you could tunnel across the barrier at room temperature if you wait 60 quadrillion, bazillion, gadillion times the age of the universe, that sort of thing. Just like, sure, I could tunnel through this. Holy crap, no, I didn't, I'm still here, because it would take, 10 to the 1000th power or something Hubble times to tunnel through a wall for something the size of so whatever it is, that sort of thing. Sure, I could. If I did, then I would know that I live in a many worlds universe because that's so improbable that the only explanation is that I'm in that instantiation of me that tunneled through the wall is that exceedingly rare. It's in that exceedingly rare subset that actually does the tunneling. That's really not going off into woo, but yeah, anyway. All right, break time.
Quantum stuff is so cool. Why does it have to be so difficult?